Well, greetings, mathletes, and welcome back. In our last episode, we took a look at equation solving, and we're going to continue that today, and we're going to start looking at some of the more complicated examples, and when you have more than one operation and things build up. So, before we get started, there's some things I want to lay down first that we need to remember. Okay, so one of those things is just quick review from last time. We want to remember that addition and subtraction undo each other, and multiplication and division undo each other. So we want to remember those things first. Now, one of the things that we're going to need to use during today's lecture is something called the distributive property. Right? What the distributive property does is it tells us how multiplication and addition play together. There's usually a lot of rules for multiplication, a lot of rules for addition. This is combining both operations together and getting a rule out of it. And so basically what it says is that if I have some quantity, right, some number multiplied by a sum or a difference, right, that could be a subtraction also, and it still works. What you can do is multiply each term individually. So each term in the sum gets multiplied individually. A times B is AB, and A times C is AC. And then you have to honor the signs, right? So that's a property we're going to be using today. I imagine that there's a decent portion of you who are already familiar with it, but I just wanted to go over it one more time, what the property is. And now looking at an example of how this works, if I have something like 2 times 3x minus 5, right, what that means is I'm going to take this 2 and I'm going to multiply it times the 3x to get 6x, and 2 times the negative 5 to give me a negative 10, right? And so now we've distributed this. Okay, so that's the idea of distribution. And we'll get plenty of practice with this because it's going to show up in a lot of the problems, which is why I'm not doing too many examples of these intro ideas. And then the other idea is the ability to collect like terms. So like terms are terms that have the same variable part, right? So they're either they're both constants, like 3 and 5 are both constants. You can consider those like terms and combine them into an 8. But even if I had a variable on here, as long as it's the same variable and I have the same number of each variable, what I end up with is 8x, right? Because this is telling me I have 3 x's here, I have 5 more x's here, so altogether I have 8 x's. So it's telling you how many of what you have. And then, of course, you can combine these things together, right? If I end up with 3x minus 2 plus 7x plus 1, basically what I can do is find the things that have the same variable part and add them together. So 3x and 7x have the same variable part. Those are like terms. So I can add them together. 3 plus 7 is 10. This gives me a 10x. Negative 2 and 1 are both constants. And so that makes those like terms. And I add those together. Negative 2 plus 1 is negative 1. And so this would simplify to 10x minus 1. All right. So that's kind of the preliminaries as far as tools that we have to use. Now, the other thing I want to talk about is more of a what if kind of a thing. There are certain times in equations that you get really weird answers, right? Or weird things happen. So there's some weird things here. So sometimes when you're trying to simplify an equation, so you'll start with an equation, you simplify, and the variables go away. Variables vanish, right? This happens, and we will see examples of it. I'm going to keep it a little bit vague for the moment right here. There are two things that can happen. If your variables vanish, that means you're down to just numbers. That means you have no variables left. So two things could happen. If your variables vanish, you will either have a true statement or a false statement. So if it's a true statement, right, if you have a true statement, you'll get things like 0 equals 0. That's not a 0. 0 equals 0. Negative 2 equals negative 2. 10 equals 10, right? You get stuff like this, right? No, there's no variables in it, but you have two things that are absolutely equal to each other. Okay, this means that it is definitely a true statement, right? Because things like zero does equal 0, and there's nothing you can do about it, right? There's no place to plug in a variable and change the value of one side. 0 equals 0, negative 2 equals negative 2, 7 equals 7. When you get something equal to itself, that's called an identity, right? So that's terminology you need. What it means is that the solutions are all real numbers, right? And there's a symbol for that. So I'll probably be using that throughout the lecture. The symbol for all real numbers is an R with the spine double stamped, right? So it's an R with a double stamped spine. Okay, so that's this. And actually, I just realized I organized this poorly. This other branch was supposed to be the other thing that happens. The other thing that happens here is you get a false statement. Right? If you get a false statement, you'll get things like 0 equals 5, 4 equals negative 3, 2 equals negative 2, right? Things that are definitely not equal to each other. Okay, now if I do that, and I'm going to move my happy little face here. If that happens, right, you know it's a false statement because these things aren't true, and there's nothing you can do about it because there's nowhere to plug in a variable to change values. This is called a contradiction. I hope I have room. Oh, I'm going to run out of room. Okay, try it again. There we go. That didn't change anything. Okay, it's a contradiction. We'll just go with that. If you have a contradiction, that means there are no solutions, right? And there's a symbol for that too. It's actually the symbol for an empty set, which is a circle with a zero with a line written through it. So if you're in the habit of writing your zeros with a line through them, that's more of an accounting thing, like business accounting, so that you can tell the difference between an O and the number 0. It's really not a good idea in math because what it means when you write it in math is that there isn't a solution at all. So, and 0 can be a solution. So you want to be careful with that. So that's the main thing there. This is the main thing I want to try that again. The main thing I want to emphasize is that if your variables go away, there are two possibilities. Now, I don't think we're going to have a good understanding of this until we see an example of it. So we will come across an example of this as we go through the lecture here. All right. So let's go ahead and clear that out. And then I'm going to move myself back over here. And we'll take a look at the next example here. Okay, so Our first example is just going to take us a little bit past what our last lecture had us working on. If we look at, oh, turns out this works better with the, there we go. If we look at our first example here, oh, excuse me. Right, and we think about the differences we see compared to last time. Basically, the big difference is there are two operations holding x back, right? Because really our goal in and you want to be thinking about this in terms of goals because the steps change every single equation. So you want to think about what your goal is. Your goal is to get variables on one side, numbers on the other. Right? We want variables on one side, numbers on the other. So let's see how far we've gotten as far as that goal is. Because really, we want to get to the point where we can just say x equals something, right? Some number. I'll just call it a because we don't know. Yeah, our goal is to get x on one side by itself. Well, let's look here. I have all the x's on one side, but I have things that are in the way. So if I'm going to solve this, well, actually, let's just see what you know already. Go ahead and pause here and see if you can work it out. Okay. So if we take a look at this, what we would start with is trying to peel this minus 12 off. Now, if I'm going to peel off a minus 12, I'm going to use the undoing function, plus 12, and I have to do it to both sides. And so if I do it to both sides, let's see here, that gives me 4x, right? And then the 12s cancel, and 24 plus 12 is 36. And so you notice that step was just like the steps we did before with addition. It's this time, instead of just having an x by itself, we have a 4x we got by itself. But now we have all the x's on one side and numbers on the other, and we're down to the one-step equation that we looked at last time. I have 4 times a variable equals 36. And so if I want to take this off, it's attached by multiplication. I divide. Right? And that cancels, and I get x is equal to, well, let's see, 36 divided by 4 is 9. So x equals 9. Okay, so are there any questions about that? Yeah, I got a question, Mr. Brian. I divided by 4 first, and I got 18. Well, I think that was more of a statement than a question, but let's take a look at that because that is a good observation. So I'm assuming you did this. Let's go ahead and rewrite the problem. So you're saying you divided by 4 first here, right? And that canceled, and you got x minus 12 is equal to 6. Is that right? Yeah, that's what I did. Okay, well, here's the problem with that. When you're looking at this, right, you can divide by 4 first. It's usually not very practical because what you end up having to do, you have to divide the 12 also. You can't just divide the term that has the x in it. It's got to be every term through the whole thing if you're going to divide. So here's why that didn't work, because I can see what you did here. You added the 12 over and you got 18. What should have happened here, if you were going to divide by 4, you divide the whole side by 4, right? That does give you your 6 on this side. This turns into 4x over 4 minus 12 over 4. And that cancels because 4 divided by 4 is 1. This turns into a 3, and I end up with x minus 3 is equal to 6. And now if I add 3, I get x is equal to 9. right? Which is what we got in the first place. But you have to divide the whole thing. And you can probably see where you're going to run into trouble. Um, if this number wasn't divisible by 4, then this fraction wouldn't reduce. And you just put fractions in something that you didn't need fractions in. So it's not technically wrong, but if you don't do it correctly, it will give you the wrong answer. So you really do want to start with undoing the addition first, additions and subtractions first, then look at multiplications and divisions, see what you can do about those. But there's a lot of different ways to do these. And sometimes the thing that works for one doesn't work for the other, and you have to do it a different way. So, all right, so let's go ahead and take a look at the next example here. And okay, our next example, let's take a look at this here. We got, oh, here we go again. Let's say 2 times x plus 1 is equal to 3x. Okay, so let's say we're taking a look at this. Now you notice this does look different than what we've seen before. There's things trapped in parentheses. Well, this is why I brought up the distributive property earlier. What we're going to end up doing is taking this 2 and multiplying it by each of the terms inside the parentheses. So from here, this is going to give me a 2x plus 2, right? Just multiplying that out. And then the other side is equal to 3x. Now, remember, our goal is to get our x's on one side and our numbers on the other. We have x's on both sides, right? So that means we have to pick a side. It actually doesn't matter whether you decide to move them all to the left or move them all to the right. In fact, I'll work this one out both ways so you can see how each one results. There are times it's easier to move it to one side or the other. Now, to start out with, I think most people are used to seeing x move to the left side of the equation just because, and I think the reason we do that is just because that's how we organize sentences in English. The subject of the sentence usually comes first. And so we feel like x has to come first since that's what we were looking for. But there's no law about it in math. If x is equal to 2, then 2 is equal to x, or however it works out. So in any case, from here, I'm going to choose to move everything to the right-hand side of the equation. So I'm going to move these x's, and you can just subtract them over. As long as we do it to both sides, we can add or subtract anything to an equation. Most of the time, if you're just doing it willy-nilly, it doesn't help you, but you're always allowed to. Okay, so 2x minus 2x is 0. And that leaves me with a 2 on the left-hand side. If I have 3x minus 2x, well, I have 3 minus 2. That leaves me with 1x. And we write 1x as x. Right? So 2 equals x. Oh, I guess I said the answer. I was just picking a number out of the air. So either one of these answers are the correct way to write it. Okay? Now, let's look at what happens if you decide to move the x to the left-hand side. Now, the first step is still the same, so I'll just start with what we have here. Okay, so if I choose to move the x's to the left-hand side, that will give me minus 3x minus 3x, and 2 minus 3 is negative 1. So this leaves me with a negative x plus 2 is equal to 0. Okay, we still don't have x by itself. But we do know how to get rid of that too. We'll just subtract it from both sides. Right? That cancels, and I get minus x is equal to minus 2. There's a real temptation to say x is equal to negative 2 here. That x is not equal to negative 2. Negative x is equal to negative 2. We need x to equal negative 2. And so there's a few ways to look at this. Keeping in mind that negative x really does mean negative 1 times x. You could either look at it as multiplying or dividing it off. Either way, it's probably more consistent with what we've been doing, dividing it off, right? Anything divided by itself is 1, so that gives me an x. And then negative 2 divided by negative 1, well, it's a negative divided by a negative. That comes out to positive 2. And so you can see, because when we moved it to the left-hand side this time, we generated a negative that that we needed to deal with. So oftentimes your choice of how to move the x will determine whether or not you end up having to divide by a positive or dealing with a negative at some point. You can avoid negatives if notice that this value is less than this value. So if I subtract it, I end up with the positive x. So if you always subtract the smaller one from the bigger one, what you'll end up with is a positive coefficient of x. And then you don't have the extra negatives to think about. And oftentimes it saves you steps too. Okay, excellent. So let's go ahead and clear this one off. Okay, so let's walk through the next example here. So let's say I have 2 times, oh, let's switch the color. There we go. Once again, there we go. 2 times 3x plus 5 is equal to 4 times x plus 2 minus 3. Okay, so we're going to see what we can do with this one. We're going to walk through this one together, and we'll take a look at another one after this. So let's see what we got here. Now looking at this again, my goal is to get the x's on one side and the numbers on the other. I need to be able to get to the x's in the first place. So I am going to distribute. That gives me 6x plus 10 on the left-hand side. And if I distribute on the right-hand side, because they don't affect each other, so I can do them simultaneously, that leaves me with 4x 4x plus 8 minus 3, right? And you notice after I distributed, I no longer need the parentheses. Okay, so if I collect my like terms, 8 minus 3 over here, well, I'm going to write this side. 8 minus 3 is 5, so this is plus 5. Okay, so now we have to make some choices. We have to figure out which side I want to move the x's to, which side I want to move the numbers to. Well, I have 6x's over here, and I have 4x's over here. And so if I subtract the 4x's from the 6x's, I'll end up with a positive 2x. If I go the other direction, subtract the 6x over, I'll end up with negative 2x. And so it's a little easier to deal with the positive numbers. So I'm going to subtract 4x from both sides. And so that should leave me with, let's see, that gives me 2x plus 10. That cancels, and that's equal to 5 now. And you notice this is the same form as the first example I gave you today. I have a number times a variable plus a number equals a number, right? It's the same form. And once you get here, it's just a matter of moving the numbers to one side and finishing to peel off the layers of x. So let's see here. That gives me minus 10. I'm going to subtract 10 from both sides now. So I get 2x is equal to, let's see here, that's negative 5. Oh, I can't write the answer yet. We haven't done that step. Sorry, I'm getting ahead of myself. So that's negative 5. And then once I divide by 2 here, I end up with x equals negative 5 halves, right? It's absolutely legitimate to come up with a fraction for an answer. Okay. So now that we've seen that, let's go ahead, let's clear this off, and we'll look at the next example. Okay, so here's our next example. Remember what, and this is for you guys to work on. Remember what you want to do is you want to distribute, right? You get everything distributed first, collect like terms, right? And then start sorting the variables and numbers, right? So that's sorting left and right. Variables, numbers, pick a side for x, pick a side for numbers, and just start working that direction. Okay, so go ahead and pause it here, and then we'll discuss the problem once you finish and push play again. Okay, so you're back. So I'm assuming we want to take a look at this. So if we go ahead and start on this, well, actually, before we start, did anyone notice anything strange about this problem? Oh yeah, Mr. Bryan, all my X's went away. Isn't that all we can really hope for is our X's to go away? Yeah, but math. Okay, math. Okay, so let's just take a look at what that means. So our X's did go away. Let's look at how that happened when we work on this. Okay, so starting out, we would need to distribute everybody first. So we're going to distribute here. That's going to give me 5x minus 10 plus 3x equals, you don't want to misplace that equal sign. Make sure you write it down each time. If you miss it, you start getting weird stuff happening with your equations. And then we want to distribute here also. So that's going to give me 8x plus 2 and then minus 12. Okay, so let's go ahead and start collecting our like terms. We've gotten all our distribution done. Let's see here. So over here I have 5x and 3x. That gives me 8x minus 10. And then over here, let's see, 8x doesn't have any friends, but 2 minus 12 is minus 10. And yeah, I can see something's going on here. If I go ahead and subtract out 8x here, what I end up with is negative 10 equals negative 10, right? And so our x's did go away. It's not just something you hope for when you're dating and stuff. Yeah, and if we remember what I was talking about at the beginning, this is one of those cases where your variables vanish, right? And if your variables vanish, you have two cases. You either have something that's true or you have something that's false. This case, we have a true statement. Negative 10 does indeed equal negative 10. And so since this is a true statement, right, we know it's a true statement, so the solutions are all real numbers. Right? You're going to get all real numbers. What that actually means, if you say all real numbers are the solution, that means any number you pick, no matter what it is, if you plug it in for x in this original equation, if you plug any number in for x, you will get a true statement out of it. So basically what it's saying is that there is nothing you can do to make this equation not a true statement. It doesn't matter what you plug in for x, it's going to disappear, right? So no matter what you put in for x, it disappears, and negative 10 is still equal to negative 10, right? Okay, so this one actually has solutions that are all real numbers, right? This is not your solution. This is your solution, right? So that's that's one of the things that happens when your variables disappear. And if we remember the other one, if instead of let's kind of section this off. Instead of a true statement, if I had gotten something like negative 10 equals 3, well, that's not true. And if you get something that's not true, you have no solution, right? You have zero solutions. It means that circle with the slash through it is the empty set. It means if you collect all the solutions together, the set of solutions is empty. All right. Well, good. Good, good, good. So let's go ahead and clear this off and take a look at the next example. Okay, so this example is going to change it up a little bit. There we go. Let's go ahead and take a look at, oh, I don't want that color. Let's try it again. Oh, let's try it. There we go. There we go. Now we win. Okay. There we go. So let's see here. And we are changing it up a little bit here. You already notice what's going on. Mr. Bryan? Yes, I like your beard. Thank you. Yours is nice too. Okay, so let's get to the math here. Now, here's what's different about this. I'm sure you already picked it out. We have fractions in here. Okay, so what we're gonna there are different ways to do this. I could certainly, 5/8 is a number. I could subtract 3 from 5/8, find a common denominator, do that whole business, and go through that way. But there's a really nice trick to get rid of fractions, so you don't have to deal with them at all. And so here's how the trick works. First of all, you want to remember that any whole number you have is actually over 1. Okay, so now what we do is we look and ask ourselves, what between 2, 1, and 8, what would the common denominator be, right? Between those three things. 8? Right, it's 8. Now here's what we do with it. This is what's different. Every term is going to get multiplied by the common denominator. And it has to be the common denominator. It has a particular effect that won't happen unless you use the common denominator. So we agreed that 8 was the common denominator. Everyone gets multiplied by 8. And if it helps, this is 8 over 1, right? You want to be thinking about it that way. You can do that too, although it doesn't matter here because they're both whole numbers, but we can do the same thing here. Now, the effect it has is it clears out all of the denominators, because the property of a common denominator is that all of the denominators divide into it. So if we multiply by it, what we can do is this. This 2 cancels with this 8 to give me a 4. And so now I can multiply the 4 times the 3 to get, we'll write it in a different color, 12 times x plus 3. Mr. Brian, why didn't we multiply the x plus 3 by 4 also? Because they're both there. That's actually a really good question. So when we're looking at this, really what this is boiled down to is now 4 times 3 times x plus 3. Right, when you look at that whole thing, because it's the 4 times the 4's up here, 4 times 3, and then I have the x plus 3. So it's 3 things being multiplied together, right? I'm not going to worry about this addition at this moment. So anytime you multiply 3 things, if instead of x plus 3 it was just a 2, if I had 4 times 3 times 2, I would multiply the 4 times 3 first and then multiply the 2. And that's what we're doing here. I'm multiplying the 4 times 3 first and then multiplying it by this. So the 4 times 3 gives me this 12. So hopefully that answered your question. I think so, but once I see the problem, I'll know for sure. Okay, so let's continue then. So we have the 12 times x plus 3, and then over here we have this multiplication, 8 times 3. Well, the denominators are just 1s. So 8 times 3 is 24. And then the last side here, you notice the 8's cancel out completely, and I end up with just a 5. And you notice the resulting equation now has no fractions in it whatsoever. It's back to we're back into familiar waters is basically the idea. This is the case we worked on before. And so now we know all we need to do is distribute, collect like terms, and then start sorting x's and numbers. So if I distribute, I end up with 12x plus 36, and then plus 24 equals 5. And then these guys are like terms. 36 plus 24 is going to be 60. Wow. So that's 12x plus 60 equals 5. Right, so far so good. Well, now we're back to that original two-step type equation that I worked out in the first example. So I'm going to subtract 60 from both sides. And that gives me 12x is equal to negative 55. And then the last step would be to divide off this 12. Right? And so I end up with x is equal to negative 55 over 12, and we do have to see if this thing reduces. Um, so one of the ways you can check, especially if you don't see anything here, if nothing jumps out at you, is just to do a factor tree real quick. Let's see, 55 is 5 times 11. Those are both prime. So this is 5 times 11, and that's negative. And then 12, that's 4 times 3, 2 times 2. Okay, so that's 2 times 2 times 3. And you notice there's nothing that cancels out here. So that means that we were already reduced here. Right? So we got the answer, negative 55 over 12. Okay, so are there questions? So if you have fractions in the equations, that means the answer is going to be a fraction too then, right? Not necessarily. As a matter of fact, let's do this. Not necessarily. Just because there's fractions in the original equation doesn't mean there's going to be fractions as in your answer. And also, if there's not fractions in your equation, there could very well be fractions in your answers. So every equation could give a whole number or a fraction answer, and it doesn't matter whether there's fractions in the equations or not. Okay, does that help? Okay. Yeah, I think so. Um, I don't like fractions, Mr. Bryan. Yeah, I don't like doing dishes, so, but things have to get done. Yeah, I guess. Well, remember, fractions are your friends. I think they're more like my enemies. Well, you know what they say, keep your friends close and your enemies closer. So, there's really not too many ways around it. I really like this trick though. I mean, if you don't like fractions, fractions are your friends, but they can overstay their welcome just like anyone else. So if you have a way of clearing them out so that you don't have any fractions to deal with, that's great. And that's why I just showed you this method, because it's one of those things that it does pop up a lot where you have fractions, and it'd be really nice if you could just get rid of them. So yeah, there's no way around it. We just have to learn it. I'm not bashful about fractions, so they are definitely going to pop up. You could have fractions pop up in any problem at any time, right? I am not afraid of them whatsoever. In fact, if I allow the answers to be fractions, it makes it a lot easier to write equations too. All right, but thanks for the tip. That the trick with the fractions and stuff. Um, yeah, I think that's a good trick. Thank you. Well, you're welcome, and I hope it helps. I do want to look at one more example before we finish up here. So, oops. Let's try this again. Ding. There we go. All right, so we cleared that out, and let's see here. Where's the last example that I wanted to do? Okay, yeah, and this one will be for you guys to play with. So let's say I have 2x over 4 plus 3 equals x over 2 plus 3 fourths. Yeah, we'll do that one. I think that would be pretty good. So here's what I want you to do. I want you to go ahead and pause the video, take a stab at it on your own, see if you can walk through it, and then I'll work out a complete solution after this. Okay? So go ahead and pause here. All right, so you're back now. Let's go ahead and take a look. So in the interest of getting rid of fractions, I can multiply by the common denominator, and I have to multiply every single term by the common denominator. In this case, it would be 4. Use the force. Okay, so once I multiply by 4, I can start canceling some of this stuff out, right? This 4 cancels with this 4 to give me 2x. 4 times 3 is 12. 2 cancels with 4 to make a 2. So this gives me a 2 times x, right? Because that's what's left. And then over here, the 4's cancel to give me a 3. Okay, so we're here. Now, we'll go ahead and try to move the x's to one side, numbers to the other. I'm going to choose to the left this time for the x's. So minus 2x, minus 2x. And we'll notice the next line here, that cancels with that. These guys both cancel out, and I end up with 12 equals 3, right? And that's a lie, right? This is a lie. That's not really a math term. But 12 does not equal 3. And remember, we talked about when our x's go away, we look to see whether we have a true statement or a false statement. This thing is totally false, right? It is not true. 12 is not equal to 3. And what that means is we have a contradiction. Or you can also say that there's no solution, right? Because what that means is no matter what I plug in for x, it cancels out while I'm computing it. It completely cancels out, and I end up with 12 equals 3, which is an absolute lie. And so what that means is nothing you plug into this will work. This statement has no way of making itself true. And that's really the idea here. Okay. So we have, excuse me, we've walked through the rest of our equation solving as far as the introduction goes. And in any case, this should get you going for your homework. If you have any questions, please feel free to stop by and see me. And until next time, keep your wits and your pencils sharp.